Bismillahirrahmanirrahim. Let's start our next lecture for heat and mass transfer. We are Alhamdulillah now going to start chapter number 3 of our book Incorpora and Divot, and the title of this chapter is One Dimensional Steady State Conduction. Again, we would be covering in fact two major topics in this chapter. And this chapter will take a little bit longer as compared to chapters 1 and 2. It is longer, but it is not difficult at all. It is a very interesting chapter. There are two major topics. One topic is that of the thermal networks, and under the thermal networks topic we would be discussing the temperature distribution in case of a plane wall, in case of a cylinder, and in case of a sphere. So we would be finding out temperature distribution means T as a function of X, because most of the cases, most of the times we would be dealing with one-dimensional heat transfer cases. So in the case of plane wall, we would be finding out the temperature distribution means an expression relating temperature with X. Similarly, in case of cylinder, we would be developing a temperature distribution means T as a function of R, and similarly in case of a sphere it would be the same, means we would be developing an expression of temperature in terms of radius. And then the next topic is after temperature distribution is in fact the resistances. So far you are aware of the electrical networks and electrical resistances using Ohm's law, V is equal to IR. So we would be using the same analogy, and we would be determining the, and we would be focusing upon, and we would be discussing the thermal resistances. So there would be various types of thermal resistances. First of all, conductive resistance in the case of plane wall means in case of Cartesian coordinate system. And then we would be discussing the conductive resistance in case of cylindrical coordinate systems, and then in the case of spherical coordinate systems. Along with the conductive resistances, we would also be discussing the convective resistance and the radiative resistance whenever the convection will take place and whenever the radiation heat transfer will take place. Along with the thermal networks, the next topic that this chapter has is the heat transfer using fins. Probably you might know that fins is a device, it is in fact a protrusion on the original assembly, on the original body, which enhances the heat transfer rate. So we would be discussing various concepts, various numericals on fins, on heat transfer enhancement using fins. With the Cartesian coordinate system, and the title is the temperature distribution in a plane wall. We will see how the things go. So starting with the heat diffusion equation in Cartesian coordinate system. Whether we do it for Cartesian coordinate system, a plane wall, or cylindrical coordinate system, or a pipe, or a spherical coordinate system, the sequence of the steps would remain the same. So the first step is to start with the heat diffusion equation. Since we are going over plane wall, so we are starting with the heat diffusion equation in Cartesian coordinate system, which is dou by dou x of k dou t by dou x, the similar term in y, similar term in z, plus q dot is rho c dou t by dou t. Now if we say that the system is such, means the plane wall is such that the heat transfer is one dimensional, so we have a temperature gradient in one dimension only, for example x or y or z, you can take any dimension, we will take x. There is no internal heat generation in the wall, the system is working under steady state conditions, and the thermal conductivity is constant. So the second term will vanish, the third term will vanish, there is no internal heat generation in the system, and the system is working under a steady state condition. So we will be left with one term only, which is dava by dava x of k dava t by dava x, which can then be written as d. Dava can then be replaced with a d. And this discussion has taken place before, that if this is equal to 0, so then temperature is a linear function of x. Why? Because if we have a linear function and if we differentiate it twice, so therefore its second differential will be 0. For example, if y is equal to a plus bx, then the first differential would be b and the second differential would be 0. And the heat flux is constant. And how the heat flux is constant? Because this thing is in fact the heat flux. Q is minus Ka dt by dx. So Ka dt by dx without area would be heat flux. So what it says is that the change in the heat flux is 0. If the change in the heat flux is 0, it means that the heat flux is a constant quantity, right? Now if we say that the thermal conductivity is constant, so K will come out of the differential sign and then 0 upon K will give us 0. So we will be left with d by dx of dt by dx as 0. So whether it is plane wall or cylindrical coordinate system or spherical coordinate system, we will first start with the heat diffusion equation and we will make those four assumptions, or we will say again that it is not an assumption, rather it is how the system is working under. So we would be left with one term only. And now if we integrate this equation, so the first integral will remove this differential sign, right? So we will be left with dt by dx on the left hand side and integral of 0 would be a constant. And if we then integrate it again with respect to x, so the integral of dt by dx would be t, just like integral of dy by dx is y. Integral of c1 would be c1x, and then there would be another constant c2. So t is c1x plus c2. Now what we would be doing over here and in cylindrical and spherical systems as well, that we would be finding out the values of c1 and c2. These are the two unknowns. So we need to find out c1 and c2. Now since there are two unknowns, so we would be needing two boundary conditions. So in the case of plane wall, the two boundary conditions that we would impose are those: at x is equal to 0, t is t1, and the second boundary condition says that at x is equal to L, t is t2. What does this simply mean? It simply means that we know temperatures at the two faces. At this face of the wall, the temperature has a value of T1, for example 100 degrees Celsius, and at this face of the wall temperature is T2, for example 40 degrees Celsius. So we are only saying that we know temperatures at two locations, and the same boundary conditions would be there in the subsequent cases, means cylindrical and spherical. Now if we apply the first boundary condition in equation 1, so we will put the first boundary condition says that at x is equal to 0, temperature has a value of T1. So in place of x we will put 0 and in place of t we will put T1. So T1 is C1 times 0 plus C2. So we will immediately get C2 as equal to T1. We will get immediately get C2 as equal to T1. And if we then put the second boundary condition in the same equation 1, so the second boundary condition says that at x is equal to L, L is this thickness of the wall. L is in fact the thickness of the wall. We may call it L or we may call it delta x, whatever. So if we put this second boundary condition in equation 1, T would be written as T2, and in place of x we will write L plus C2, and C2 is equal to T1. So in place of C2 we can then write T1. So from here C1 would be T2 minus T1 over L, would be T2 minus T1 over L. Now we have found out the values of C1 and C2. See, C2 and C1 are both in terms of known quantities. We know T1, we know T2, and we know the thickness of the wall. So there is no variable or any unknown quantity in here. So if we then put C1 and C2 back in 1, so T would be equal to C1x. C1 is T2 minus T1 over L. C1 is T2 minus T1 over L. And C2 is equal to T1. So in place of C2 we have written T1. So this is the temperature distribution in a plane wall if it is one-dimensional heat transfer, if there is no internal energy generation in the wall, if the thermal conductivity is a constant property, means the material is isotropic, and if the system is working under steady state conditions. And you can see that in fact T is a linear function of x, because T2 and T1 and L are constants and T1 is constant as well. So in fact it is written as T is equal to mx plus c, so or ax plus b. So in fact T varies linearly with x, and therefore you can see that this curve of temperature Tx, this is in fact T or Tx, means T as a function of x, is in fact has been made linear. If any of those four conditions is relaxed, of course then it will not be a linear equation. And we have seen some non-linear equations in chapter number 2, such as a plus bx plus cx square, etc., etc. Now starting with the Fourier's law of heat conduction, which says Q is minus Ka dt by dx. So minus Ka d by dx of temperature. So we need to differentiate temperature with respect to x. So if we want to differentiate y with respect to x, we need y as a function of x. So if we want to differentiate temperature with respect to x, so we need to have temperature as a function of x. And where is that function? This is that function. So we will put this whole function in here. So if we now differentiate this thing written in the square brackets, the differential of mx would be m, means T2 minus T1 over L, and the differential of T1 with respect to x will be 0. So we will get Q as minus Ka T2 minus T1 over L. And if we then take this negative sign in here, so we can then write it as T1 minus T2 over L. It means temperature will flow from a higher, heat will flow from a higher temperature of T1 to a lower temperature of T2. And if we then write, kindly listen very carefully, that if we now write this in such a form that we only keep delta T in the numerator, and we take the rest of the parameters in the denominator. So we will have T1 minus T2 in the numerator, and the denominator will then be written as L over Ka, because this Ka can be taken over there in the numerator. So we will have the same equation again. And if we then compare this equation with V is equal to IR, the famous Ohm's law, or I is equal to V over R, we will realize that in case of electrical circuits, the quantity that flows is the current. Now what we are going to do is that we are going to introduce thermal resistances, thermal networks, just like we had, or we used to have electrical networks, electrical resistances. Now we would be having thermal networks and thermal resistances. So what happens in an electrical network is that this is an example of an electrical network, right? So the quantity that flows is the current in case of electrical circuits. Now the quantity that will flow in thermal circuits would be heat, would be Q. In electrical circuits, the current flows due to potential difference, voltage difference. The heat will flow due to the temperature difference. The driving potential for heat is the temperature difference, right? So you can see over here that we have the voltages at the nodes of an electrical network, whereas in case of a thermal network, we would have temperatures at the nodes. So this temperature difference will in fact be the driving force for the heat flow, and whatever is there in the denominator is the resistance. Whatever is there in the denominator is the resistance. So therefore whatever we have in the denominator, L over Ka, would be the resistance. So L over Ka would be the thermal resistance, because we are dealing with thermal networks. It is conductive in nature. Why? Because we had started a little bit earlier with the Fourier's law of heat conduction. So it would be conductive resistance. And since we are dealing with the plane wall, means we are dealing with Cartesian coordinate system. So therefore the thermal resistance offered by a plane wall, the thermal conductive resistance offered by a plane wall, means in Cartesian coordinate system would be L over Ka. So L over Ka would be the resistance offered by, it would be the resistance, thermal resistance offered by the medium, offered by the wall. Now that wall may be a copper wall, or that wall may be a steel wall, or that wall may be a wall of brick. Whatever that wall is, wall means we are dealing in X, Y and Z. This is what the wall means, I mean the plane wall means, or the Cartesian coordinates mean. So you can write it as R, or you can write it as RTH, where RTH would denote the thermal resistance. Kindly note that this is not the thermal conductive resistance in cylindrical coordinates, because in cylindrical coordinates and in spherical coordinates we would be dealing with radius, right, inner and outer radius. So we will come to that point in a bit. Now if we go to convection expression, and if we write the Newton's law of cooling as HA delta T, and if we do the same thing again, means if we write this equation in a manner such that we only keep delta T in the numerator and then we take the rest of the parameters in the denominator, so then we would write it in this form, 1 over HA. Because if we take HA in the numerator, it would again become HA times Ts minus T infinity. If we then compare it, this equation with V is equal to IR or I is equal to V over R, we will realize that the quantity that flows in electrical circuits is the current, whereas the quantity that flows in thermal circuits is the heat. Current flows due to potential difference, voltage difference, whereas the heat will flow due to the temperature difference, which is there in the numerator, Ts minus T infinity. And whatever we have in the denominator is the electrical resistance in I is equal to V over R. So therefore whatever we have in the denominator, and what we have in the denominator is 1 over HA. So this would be the resistance, but this would be the thermal resistance. This would be the thermal resistance, and it would be convective resistance, 1 over HA. Over here you will note that we have not used Cartesian. The reason is that if I ask you that what would be the expression for convection if the fluid is flowing over a flat plate, you will say HA delta T, and the same expression is used if the fluid flows over a cylinder or a sphere. So this 1 over HA is the thermal convective resistance, and this resistance is independent of the coordinate system. This 1 over HA convective resistance is in fact independent of the coordinate system. However, the conductive resistance depends upon the coordinate system, whereas convective resistance does not depend upon the coordinate system. However, if we see what will change, if it is a wall, if it is Cartesian coordinate, so area would be length by breadth, one side by other side. If it is cylinder over which a fluid is flowing and convection is taking place, so then area would be 2 pi RL. If it is the sphere over which a fluid is flowing and convection is taking place between that fluid and the outer surface of the sphere, then area would be 4 pi R square. So it is area that will change with respect to the coordinate system, but in general 1 over HA would be the convective resistance. Similarly, if we start with the expression for radiation sigma epsilon A T14 minus T walls 4 or T surrounding 4. If you recall, we had then written it in this form HA delta T, similar to convection equation. But this, and how did we write it? We had performed the factorization of A4 minus B4. It was A square plus B square and then A square minus B square. And then we had performed factorization for A square minus B square. It was A plus B times A minus B. And then we had separated the area along with delta T. So whatever was left was radiative heat transfer coefficient HR. If we then write this equation in the same form, which form? Keeping delta T in the numerator and taking the rest of the parameters in the denominator, we will write it in this way. And then if we compare it with V is equal to IR or I is equal to V over R, the quantity that flows in the electrical circuits is the current, whereas the quantity that flows in the thermal circuits is the Q. It means the current flows due to voltage difference and the heat flows due to temperature difference. Whatever is left in the denominator is resistance. So whatever is left in here in the denominator means 1 over HRA would be the radiative resistance. And again, it is independent of the coordinate system because we will simply put the area of that object, whether it is wall or a cylinder or a sphere. So convective resistance is 1 over HA and radiative resistance is 1 over HRA. And these two resistances are in fact independent of the coordinate system, whereas L over Ka is a thermal conductive resistance in Cartesian coordinate system. So what is left for discussion? The thing that is left for discussion is the thermal conductive resistance in the cylindrical coordinate system and in the spherical coordinate system. This is what we will discuss in a bit. Now this is the analogy between the thermal networks and electrical networks. See, it is a wire through which the current is passing through, and the current will pass as a result of voltage difference, potential difference. So on the nodes we would have V1 and V2, and the current would then flow through this electrical resistance. The resistance would be offered by that wire through which the current is passing. Now when it comes to thermal networks, for example, over here is being shown a plane wall. The heat will flow through this wall and the heat will flow due to the temperature difference. The larger the temperature difference is, more would be the heat flow. So therefore on the nodes we would have temperatures. And it is the heat that will flow through this thermal network, where R thermal is the thermal resistance offered by this wall. So if this wall is conductive, it will offer less resistance and vice versa. For example, if this wall is made of steel, then it will offer relatively less resistance as compared to a wall of brick, because brick has got very low thermal conductivity. It is not conductive in nature. So lower thermal conductivity materials will offer very high resistance to heat flow, and highly conductive materials will offer low resistance to heat flow. And this would be the direction of heat flow, means from higher temperature T1 to lower temperature T2. If T2 is greater than T1, then the direction of the heat flow will be reversed from higher temperature to lower temperature. Over here are being shown the convective and radiative resistances. Let's start with the convective resistance. Convective resistance, as we just discussed, is 1 over HA, where A or AS is the area of the surface between that surface and the fluid the convection would be taking place, and the heat will flow, and what do we have at the two nodes are Ts are the two temperatures, means Ts and T infinity, because when we say it is convection we use Q is equal to HA delta T, and that delta T is Ts minus T infinity. So Ts is the temperature of this surface of this face, and T infinity is the temperature of the fluid which is on this side of the surface of this face. And you can see over here that if Ts is greater, this is the temperature profile, this is the temperature profile. So Ts is greater than T infinity, so that is why temperature is higher at Ts and lower at T infinity. It may be the other way around. If T infinity is greater than Ts, then heat will flow from T infinity, from the fluid into the solid wall. Now over here is being shown the radiative resistance, and what is being shown over here is that we have this face, the area of which is again A or AS, area of the surface, and the heat is flowing via convection and radiation simultaneously. So if convection and radiation are taking place simultaneously, then those two resistances would come in parallel. So it means that the thermal resistances may be in series, just like the electrical resistances may be in series. And we have seen various electrical networks in which the resistances are connected in parallel. So therefore in thermal networks the resistances may also be connected in parallel, as is shown over here. For example, if this is the wall, so then of course from this wall the convection and radiation would be taking place simultaneously. See, radiation will not be followed by convection, or convection will not be followed by radiation. Both convection and radiation would be taking place at the same time. So since they are taking place at the same time, so therefore the two will come in parallel to each other, in parallel with each other. Now let's take a look at the combined thermal network. What is meant by the combined thermal network? Combined thermal network means that we have got more than one resistances. Means over here we have got let's first take a look at this diagram, which is figure 3.1 of our book. See, we have a wall, the thickness of which is L, or you may call it delta X. If the thickness is L, the resistance offered by the wall would be L over K, and if you call the thickness as delta X, so then the resistance would be delta X over K. Now what is this L over K? In fact, it is the conductive resistance offered by the thickness of the wall. And we have a fluid on both sides of the wall. So this fluid is at a temperature of T infinity 1, and this fluid is at a temperature of T infinity 2. This is the cold fluid and this is the hot fluid. And you can see over here the direction of heat transfer. This is the direction of heat transfer. So the heat would first be transferred from the hot fluid to the wall. It will then be conducted through the wall. It will reach the other face of the wall, and then it will be convected away by the cold fluid. So there is convection on this side of the wall, and there is convection on this side of the wall, and then there is conduction within the wall, within the thickness of the wall. So in fact we have got three resistances altogether. We have got L over K, which would be the conductive resistance offered by the thickness of the wall, and we have got convection phenomena over here. So there would be a convective resistance, and the convective resistance would be given as 1 over HA. So it is 1 over H1A. And on this side we are also having convection. So we have convective resistance between Ts2 and T infinity 2, which would be given as 1 over HA, means 1 over H2A. So they have taken H1 and H2 as different. They may be same, they may be different depending upon the conditions, the type of the fluid, the velocity of the fluid, the temperature of the fluid, etc., etc. So we can see over here that T infinity 1 is greater than TS1. So therefore the temperature drops from T infinity 1 to TS1, and then it further drops while the heat flows through the thickness of the wall to a temperature of TS2, and then it further drops to T infinity 2. So therefore the heat is flowing from the hot fluid into the wall, and then from the wall into the cold fluid. And over here you can see that the temperatures at the nodes are T infinity 1, TS1, at this node it is TS2, and at this node it is T infinity 2. So 1 over HA is the convective resistance, and convection is taking place between the fluid which is at T infinity 1 and the wall face which is at TS1. And between TS1 and TS2, it is the conduction which is taking place through the thickness of the wall. Therefore the conductive resistance in Cartesian coordinates is L over Ka or delta X over Ka. And similarly between this phase and the surrounding cold fluid, it is convection which is taking place. So wherever convection is taking place, there would be a convective resistance, and the convective resistance between TS2 and T infinity 2 is given as 1 over H2A. Now how can we write Q in this case where we have more than one modes of heat transfer? See, we can, if we call this first resistance as R1, this resistance as R2, and if we call the third resistance as R3. So it's not either conduction where we can write minus Ka delta T over delta X. It's not only convection where we can write Q as HA delta T. It's a combination of more than one modes of heat transfer. So in this case Q will be written in the form of delta T over R. Where is this form coming from? Just like we wrote Q in delta T over resistance in the previous slides, and then we had compared those expressions with V is equal to IR and I is equal to V over R. So therefore we are writing Q as delta T over resistance. Now the denominator would depend upon the numerator. The denominator would depend upon how we have written the numerator. So if we have written the numerator from T infinity 1 all the way to T infinity 2, if we write the numerator as T infinity 1 minus T infinity 2, then we need to write all the resistances that fall in between T infinity 1 and T infinity 2. Now in between T infinity 1 and T infinity 2 we have R1, R2 and R3. So we will write R1 plus R2 plus R3, means 1 over HA plus delta X over Ka plus 1 over HA. However, if we write numerator as T infinity 1 minus T1, T infinity 1 minus T1 or TS1, so then in between T infinity 1 and T1 or TS1 we only have R1, 1 over HA. So therefore in the denominator we will only write R1. If we write numerator as T infinity 1 minus T infinity 2, T infinity 1 minus T2, TS2, so in between these two we have got R1 and R2. So denominator will be written as R1 plus R2. Now it is not always necessary that we always start with T infinity 1. We may start with TS1 or T1. So if we write T1 minus T2 in the numerator, so in between TS1 and TS2 or in between T1 and T2 we only have R2 in the denominator in between. So therefore we will write R2 in the denominator. If we write the temperature difference as T1 minus T infinity 2, so in between these two we have got R2 and R3. So the denominator will be written as R2 plus R3. And if we write the numerator as TS2 or T2 minus T infinity 2, so in between these two temperatures we only have R3. So therefore only R3 will be written in the denominator. So there are various forms that Q can be written in, and all those values of Q would be the same as long as the system is working under steady state conditions. As long as the system is working under steady state conditions. So whether we calculate Q using the first expression or the second or any of those expressions, if we get 50 watts from the first one, we will get 50 watts from all the rest of the expressions, no matter what expression we use, provided there is a big if, provided that the system is working under steady state conditions. So if the system is working under steady state conditions, then the heat transferred from point A to point B will be the same as the heat transferred from point B to C, and it will be the same as the heat transferred between any 2 points. It will remain the same. See, let me give you another analogy. Consider this network as the electrical network, right? And if in an electrical network the resistances are connected in series, then what do you say? You say that the same current passes through each and every electrical resistor, don't you? So now consider this as, it means that if 5 amperes is passing through R1, then 5 ampere will pass through R2 and 5 ampere will also pass through R3. So therefore the same heat will flow through between any two nodes, if the system is working under steady state conditions. Now this is the same thing. If we call this is the same thing, means we start with T infinity 1 and then temperature of this face of the wall is T1 and the temperature of the other face of the wall is T2 and it is facing T infinity 2. Then we will have this network having 3 resistances, one of which would be conductive due to the wall and 2 of which would be conductive due to the flow of fluid over the surface. And we can then write Q in all those forms as we discussed on the previous slide. Now we are writing Q in the form of delta T over resistance, and there is another expression which says Q is equal to UA delta T. Probably you would have seen this in refrigeration and air conditioning or somewhere before, where U is called the overall heat transfer coefficient. Now if we compare the two equations, if we compare Q is equal to delta T over resistance with Q is equal to UA delta T, we can see that 1 over resistance is UA, or UA is 1 over summation of resistances if there are more than 1 resistances. So why do we call it in fact overall heat transfer coefficient? Why do we call U as overall heat transfer coefficient? Because it takes into account more than 1 modes of heat transfer, right? Over here we have got a combination of conduction and convection modes, and therefore conductive and convective resistances. There may be radiative resistances as well in some future problems. There will be. What are the units of U? See, if we compare Q is equal to UA delta T with Q is equal to HA delta T, then it will not be difficult for you to figure out the units of U. U would have the same units as that of H, means watts per meter square Kelvin. Now what are the units of resistance? See, Q is delta T over resistance. So over here resistance can be written as delta T over Q, means resistance would have units of delta T, means degree Celsius or Kelvin per watt. So units of resistance are not ohm as the units of electrical resistance, but in case of thermal resistance the units of thermal resistance is Kelvin per watt. What are the units of resistance per unit area? Because many of the times we deal in heat transfer, heat flux, Q by A. So we would be coming across resistance per unit area. See, if Q is delta T over L over Ka, delta T over resistance, it may be L over Ka, it may be 1 over Ha, or it may be 1 over HRA. I am only given one example. So if it is written as delta T over L over Ka, then L over Ka would be delta T over Q. L over Ka means the conductive resistance would have the units of Kelvin per watt, and it would be delta T over Q. Now if we take if we write the resistance without area, so therefore area will go into the numerator of the right hand side, so it will be multiplied with delta T over Q. So what are the units now? The units are now meter square times Kelvin per watt. So therefore the resistance per unit area would have the units of meter square times Kelvin per watt. And similarly the units of resistance per unit length would be meter Kelvin per watt. So I have shown you that if you are given that the resistance is Kelvin per watt, so it means you are given the total resistance. However, if you are told that the resistance is 0.1 meter square Kelvin per watt, it means that it is the resistance, it is not the total resistance, rather it is the resistance per unit area. So you need to keep an eye on the units of resistance, Kelvin per watt, and if it is resistance per unit area, it will be multiplied with area, and if it is resistance per unit length, Kelvin per watt will be multiplied with meter or whatever the units of length are. Now in here we have got a different type of wall. It's not that different. This wall is in fact composed of two materials. So we have a wall which is made of a material having thermal conductivity of K1, and we have another material having different conductivity of K2. So it is what we call a composite wall. Composite wall means a wall which is composed of two different materials having different thermal conductivities. And there is a fluid over here and there is a fluid on this side as well. So there would be two convective resistances due to the fluid on both sides of the wall. We can see H1 over here and we can see H2 over here. That are clear indications that there are fluids on both sides of the wall, and due to which there would be two convective resistances. There would be two convective resistances, 1 over HA, and due to this material 1, there would be a conductive resistance which would be L over Ka, which would be L1 means thickness of this material over K1 times A, and due to wall 2 material, it will also offer the conductive resistance in Cartesian coordinates, which would be again delta X over Ka or L over Ka, means L2 means a different thickness over a different material K2 times area. Again L1 and L2 may be same, they may be different, but K1 and K2 would certainly be different, otherwise it won't be a composite wall. So now again Q may be written in various forms, but all those forms would be the same as or similar as delta T over resistance. Now it depends what delta T do we take. For example, if we take, you can see over here that we have got T infinity 1 and the temperature of this face of the wall is T1. So between T infinity 1 and T1 we have got this R1 convective resistance, which is 1 over H1A. This face of the wall is at T2, so we have got T2 at this node, and between T1 and T2 is the conductive resistance due to material 1, so L over Ka, and we can then write 1 in the suffix of length and thermal conductivity. And then this face of the wall is at T3, so we have got T3 over here on this node, and between T2 and T3 we again have conductive resistance offered by material 2, which would be L over Ka or delta X over Ka, and after T3 we have got the fluid which is at T infinity 2. So between T2 and T infinity 2 convection is taking place, between T3 and T infinity 2 convection is taking place, so there would be a convective resistance, the expression of which would be 1 over HA, and H is H2. So if we write Q as T infinity 1 minus T infinity 2, T infinity 1 all the way to T infinity 2. So then in the denominator we need to write all the resistances that fall between T infinity 1 and T infinity 2. Means we need to write R1, R2, R3 and R4. And for example, if we write Q as T infinity 1 minus T2, So in between T infinity 1 and T2 there are only two resistances R1 and R2. So in the denominator we will only write R1 and R2. Again, it is not always necessary to start with T infinity 1. We can start from anywhere. For example, we can start with T2, and if we write T2 minus T3, then in between T2 and T3 we only have R3. So in the denominator we will only write R3. So there are various forms of Q. There are various forms that we can write Q in, and all those Q's would be the same as long as the system is working under steady state conditions. And if the system is not working under steady state conditions, then the different heat will flow through different materials. Again, the case of composite wall from our book, there are now three different materials. We have got material A having conductivity Ka, material B having conductivity Kb, and material C having conductivity Kc. And you can see that different conductivities will result in different temperature gradients. You can see that the slope over here is different, whereas the slope over here is different, and the slope over here is different. If we compare, for example, A and B, so we can see that in B the temperature gradient is large. The temperature gradient is large as compared to A. It means that B is offering more resistance to heat flow, and therefore there is a larger temperature difference, right? And since the temperature difference between TS1 and T2 is not as large as B, that would indicate that A is relatively more conductive as compared to B. So we can guess this thing by looking at the temperature distributions within different materials of the wall as well. What does this mean? TS4 and T infinity 4. I don't know why they have written T infinity 4. They could have simply written T infinity 2, because there are only two fluids, T infinity 1, and they could have written over here T infinity 2. But that's fine. It does not matter whether we write it as T infinity 2 or T infinity 4. So the temperature of the fluid over here is T infinity 4. So the temperature will gradually drop from TS4 to T infinity 4, and then it will remain T infinity 4. Right? So this is what this curve means, and the same thing is over here. It is T infinity, and when it comes to near the wall, the temperature will start varying because of the heat transfer between the fluid near to the wall and the wall itself. So over here again we can write Q in different forms. I have only written one form, whereas if we write Q as T infinity 1 minus T infinity 4 in the numerator, so in the denominator we will write all the resistances that fall between T infinity 1 and T infinity 4. Means we need to write all the 5 resistances, 3 of which are conductive due to the conduction of the 3 materials A, B and C, and 2 would be convective in nature due to convection over here on this side of the wall and due to convection over here on this side of the wall. So we can see that the middle 3 are conductive, L over Ka or delta X over Ka, and the 2 extreme ones are convective, 1 over Ha. Now this is a different diagram, and over here you can see that we have got the resistances in parallel. Now how can we have resistances in parallel? We have seen one example previously where convection and radiation were taking place simultaneously. Now in here what is happening in fact is that we have got a material E having conductivity of Ke, a material F having conductivity of Kf, a material G having conductivity of Kg, and a material H having conductivity of Kh. And this phase is at T1 and this phase is at T2. Now if this is the direction of heat transfer, means heat is flowing in this direction, in positive x-axis direction. So therefore heat will flow from this face through the thickness of E till this face. When the heat reaches this face, is it going into F or G? When the heat reaches this face over here, now is it from this face onwards, is it going into F or G or both? It is going into F and G both simultaneously. So therefore the resistance offered by F and G would be in parallel to each other, because from this point onwards, the heat is flowing in F and G simultaneously. So therefore the resistances offered by F and G would be in parallel to each other. And then once the heat reaches this point, so then it will, where will it go? It will go into H. So from this point onwards, it will go into H. This is one way of writing it. Kindly note that it is L over Ka, and this is also L over Ka. Over here it is L over Ka, where A is half of A, because this thickness, this area is in fact half of the total area. So therefore it is A by 2, and the same is written over here as well. Now what is happening over here? See, it is the same thing which has been made over here. From E it is going into F and then H. From E it is going into F and then H. But look at the areas. A by 2. So what they have done is that they have bifurcated it into two. One this portion and one this portion. So now what is area over here? It is A by 2 throughout. And what is area over here? It is A by 2 throughout. In the upper portion it is A by 2 throughout, and in the lower portion it is A by 2 throughout. So in the upper portion the heat will flow from E into F and then into H. From E into F into H, and the three would be connected in series. Whereas, is this all the heat? No. Half of the heat would be flowing over here, or not half, rather a part of heat would flow over here into E and then into G and then into H, into E and then into G and then into H. But look at the areas, all are A by 2. So we can either make it in this way or in this way. So we will go into much more details when we would start solving the problems on these series and parallel networks. So the resistances, the thermal resistances may be connected in series, they may be connected in parallel. How can they may be connected in parallel? If, for example, convection and radiation are taking place simultaneously from a surface. And over here you can see, you will realize that from this whole surface A, which is E, which is material E, the heat is going simultaneously into F and G. Therefore F and G came into parallel to each other.